tell me, as we dive into this journey, let's start at the basics. You've been involved with OCT since its inception. When we think about OCT, tell me about the physical principles behind the technology and how that works.
Probably we start with a simple definition, what OCT stands for. So the O is optical, the C is coherence, and the T is tomography. So think OCT as intravascular imaging, in which the energy source is laser. That's why it's optical. That laser is performing on the near infrared range. That's going to dictate the resolution and the ability of a tissue penetration of that energy. The C stands for coherence. And what it is that different from IVUS, there is no transducer at the tip of the catheter. So it's a very minimalistic design, because the only thing you have at the tip of the catheter is a fiber optic that rotates and a mirror that reflects back the energy from the tissue. And all the calculation of depth and imaging forming is not happening at the tip of the catheter, but outside the body. So it needs a reference arm, and hence the term coherence. So you know how deep you are scanning the vessel. And the last component, the T, is quite straightforward, is because you are acquiring tomographic image or cross-sectional image of the vessel. And as the catheter pulls back on the vessel, you have a full volume of the vessel.
So when you were talking about the physical principles behind OCT, you mentioned near-infrared light. How does near-infrared light work to acquire the image, and how does it compare to ultrasound?
Okay, so that's a very good point, because I think intravascular ultrasounds precedes intravascular OCT. So it's good for us to have IVUS as a benchmark for comparison, as you said. So near-infrared spatial resolution, as any other method, is you can decouple between axial and lateral resolution. So the axial resolution of near-infrared is an order of magnitude higher than ultrasound. We are talking about 10 to 50 microns versus 150, 200 microns for IVUS. Lateral resolution is not necessarily determined, is influenced, but not necessarily determined by the energy. It's more about the length and the position of the catheter. It also has a higher lateral resolution compared to IVUS, about 30 to 50 microns versus 300, 500 on IVUS.
How does something like this spatial resolution translate to something practical that we'd see in the cath lab?
Excellent point. So the first thing that comes in my mind, if we think about axial resolution, probably the best example I would give, actually two examples. One, think about a recently implanted stent, that the question is this stent covered by tissue or not, right? So if you think about one layer or a few layers of tissue, you are talking about something extremely thin in which actual resolution matters, right? So stent coverage is much better captured by OCT than IVUS, right? It's very difficult for you to know if the stent is completely bare on IVUS versus OCT that can identify 10 microns tissue growth on top of the stent. Another example would be probably even more relevant from a clinical standpoint, situation of a thin fibrous cap covering a lipid-rich plaque, right? So it's very easy for OCT to detect the regions that have so-called high-risk features of plaque, because it can detect thin fibrous cap atheroma, or TICFA, which IVUS resolution is unable to, right? So these would be examples of axial resolution. Examples of lateral resolution that I could give to you is, imagine a situation that you have two stents that are barely overlapping between each other. A lack of lateral resolution might misguide you to say, oh, these stents are overlapping. And what you have actually is a gap between them if you have a superior lateral resolution, that makes sense.
No, that makes sense. Talk to me a little bit about tissue penetration, because that's a question that I get pretty frequently in the field. How does tissue penetration with OCT compare to IVUS? And is it ever a limiting factor for you when you're doing a case?
Awesome question, and again, very relevant. We're going to continue to do this comparison, IVUS and OCT, because I think it helps people to benchmark, as I said before. So, broadly speaking, because the predominant tissue on coronary artery disease is fibrotic tissue, IVUS has more tissue penetration on fibrotic tissue than OCT. But I always ask physicians and colleagues that are on their journey to learn OCT and do more OCT, just to provoke these thoughts, like who has more tissue penetration? Is it OCT or IVUS? And the best answer is it depends on the tissue, right? So it is neither, because if you are talking about fibrotic tissue, IVUS has more tissue penetration. If you are talking about lipid-rich tissue, IVUS has much more penetration than OCT, and you're going to spin this in your favor if you are an OCT user, because that becomes a landmark for you to detect lipid. The lack of penetration helps you identify lipid. The third tissue, and probably the most relevant in terms of us being able to talk about thickness, is calcium. And OCT has more tissue penetration on calcium than does IVUS, right? So if I see 360 degrees of calcium on IVUS, a perfect ring, right? What I'm getting is the ultrasound is bouncing back on a calcified plaque and is unable to penetrate that calcium. I really don't know if I'm dealing with a very thin calcium or if I'm dealing with a very thick calcium. So OCT really adds an additional dimension when you talk about calcium, because you are not talking about arch anymore. You are combining distribution of calcium and thickness of calcium. This is extremely relevant because if you think about the lesion preparation, the only time that you really need plaque modification is when you have a combination of a high degree of calcium, arch-wise, but also thick calcium. Because if you have a thin calcium, even at 360 degrees of this calcium, it's okay. It's gonna fracture, it's gonna crack, right? So I would say that, broadly speaking, answering specific your question, IVUS has more tissue penetration than OCT because the predominant or most common plaque feature is fibrotic tissue. But probably for the tissue that matters the most, knowing how thick it is, which is calcium, OCT has an edge on that.
Putting all of this together in terms of the physics and the principles of how OCT works, and you have this laser that's rotating, creating these cross-sectional axial views, how does that translate to speed in the cath lab?
It's almost the the fact that you are dealing with an energy that is light, I mean, there is no theoretical limit on how fast you can pull back this, other than the physical aspect of the cat itself, right? So there is a torque cable pulling that length, and if we go from the first generation of OCT, the pullback was about 1 to 3 millimeters per second that resemble IVUS pullback. Second generation, you got to 10 millimeters. Current generation, we are pulling back at 36 millimeters per second. Why is that relevant? It's not for us to save a few seconds on the procedure itself, but it's relevant because as we're gonna get to image acquisition in another chapter, we need a blood-free environment. So the faster you pull back, the better is your imaging quality, increase your odds to achieve blood-free environment, and the least contrast you need to do so.
So we've talked about how the physics and principles of the technology have evolved over time. Mm-hmm. Help me understand a little bit about how the software and the systems have also evolved with the technology over time.
Yeah, it's a pretty fascinating journey, and I think you already prompted this, that you need to think hardware and software, right? And sometimes one is a little bit ahead of the other. For historical perspective, I would say that 2004 was the first commercial version of intravascular OCT that actually never made it to US. This was essentially distributed in Asia and Europe. Wasn't that practical because it required balloon occlusion of the vessel and a slow pullback of 1 or 3 millimeters. That was, they call it time domain OCT. We've changed on the lasers and the way the imaging is being processed. We got to a generation of FD-OCT, that stands for Fourier domain or frequency domain OCT. Now you have, as we just discussed, like almost unlimited speed on the laser, and then the hardware needs to catch up on how fast you can pull back things, right? So at that time is the first time that we have like consistent longitudinal view of the vessel. Mm-hmm. So now is software talking with hardware that pull back fast, about, if I'm not mistaken, 20 millimeters per second. And then the next big jump, or third generation, if we want to say in terms of hardware, got to 36 millimeters per second. Now we have an opportunity to fully segmented, automatically 75 millimeters of vessel on the fly, mm-hmm. right? So this was completely unheard of, that you have high quality, high resolution image. You don't take your gloves out. And one thing that I always trying to prompt people to think about on their journey with OCT is that yes, you are looking at cross section, but you should deal with the entirety of the pullback on what we call the L mode, and you have a perfect segmentation of the lumen for free. You don't need to manually draw lumen as you used to do on IVUS.
So when we think about the software, and when it first came out, you had automatic lumen segmentation, but the software has evolved since those early days. From the early days when we just had lumen segmentation to now, what are some of the features that have been incorporated into the software that help make it more intuitive for a physician to use?
Yeah, so I think it's fascinating to see how the software plays catch up with our clinical needs, right? Specific on Ultreon 2.0, I think there are tools that are embedded there that are truly very practical, right? So if I think about automation and segmentation, the number one feature that comes to my mind, in addition to lumen, is the segmentation of calcium. So the software not only gonna detect calcium for you automatically, but it's gonna display calcium arch and maximal thickness. And as we discussed before, calcium thickness is an important parameter if you decide to prepare the vessel prior to a stent.
So talk to me a little bit more about the calcium segmentation in Ultreon 2.0. I know AI is the big buzzword in so many spaces right now, and Ultreon 2.0 utilizes artificial intelligence for the calcium segmentation. What can you share with me about how that was developed and incorporated into this software?
Yeah, I mean, interesting. I actually was directly involved on this because we were the core lab back in Cleveland to be the kind of human gold standards for the software.
Right. So calcium was part of one of those features that was developed through your core lab. Correct me if I'm wrong, EEL is also now something that's automatically displayed along with lumen. Was that another feature that the Cleveland Core Lab worked to develop in conjunction with calcium?
That's right, and it's the same history, right? If you think about what you get automatically today on the pre-stenting, pullback is lumen segmentation that has been, as you said, since generation 1, but it's just even better and more robust now. You get calcium segmentation and you get EEL segmentation.
So those things are all really helpful for a physician when they're planning, their pre-intervention strategy. Talk to me a little bit about what the software offers an operator when they're assessing their stent post-intervention.
Yes, I think there are many features also embedded on the post-stent there. My number one highlight has always been about stent expansion, right? So the software allows you to two different ways to assess stent expansion. One that is a continuous volumetric that is independent on user-defined side branches. I would say that this would be the preferable method as a default, particularly if you are dealing with lesions that don't have a dominant side branch, because then the software is nicely tapering for you how the vessel should be. If you have a dominant side branch, then you can opt for the second expansion method that you can allocate when you expect the vessel to decrease in profile.
So, with all of these features in the software, talk to me a little bit about your experience with Ultreon 2.0 and how the system tries to intuitively walk a physician through their PCI and the algorithm with the software.
The software allows me to customize the workflow that fits more my needs, right? So co-registration is one of the examples. Another example is that we said that we can customize the way you acquire the image. I want, as a default, a faster pullback. So the software gives me that as well. We're not going to dive too deep on image acquisition now, but just to use as another example, the software allows me to say, I want automatic trigger or manual trigger of the pullback. So all these make it the interaction with the platform much more fluid. So it's packed with a lot of goodies, but you don't need necessary to go over every single step. You can customize whatever workflow fits you best.